Just can I welcome everybody now to the afternoon session of the Marine Surveying International Fest. It's good to see some more people coming online. You're most welcome. Thank you very much for joining us today. It gives me great pleasure to introduce someone who I regard as a friend of the IMS, really, John. And John, you've done a lot with us in the last couple of years. I'm truly grateful for the support you've given us, both in terms of financial support, but also in terms of coming to attend practical training sessions where we get to play with your ultrasonic kit and so on and have some fun. So without further ado, John, the floor is yours, and I'll leave you to deliver your presentation.
Okay, thank you, Mike. So good afternoon, good morning, good evening, wherever you may be in the world. My name is John Sharland, and I'm talking to you today about ultrasonic thickness gauges. I represent a company called Tritex NDT, who are manufacturers of multiple echo ultrasonic. Okay, I'm not sure. Okay, I just had a mute problem come up there, but it looks like I'm back on track now, so I hope everybody can hear me. So, as I say, the presentation is going to cover the principle of operation of ultrasonic thickness gauges, and we'll take an in-depth look at multiple echo gauges, probes, couplant, data logging, and when you can't get measurements, so that hopefully it would help you out if you're in a tricky situation. We're also going to have a quick look at GRP measurement and also the current products that are available today. So to start with, what is a thickness gauge? Well, it's an electronic instrument, of course, and it uses a piezoelectric crystal to measure the material thickness from one side only. Now that has a big advantage in the fact that you can take measurements wherever you like on a plate. You're not restricted to just the edge of a plate with verniers, for example, or calipers. And of course, you can take it from one side only, so you can either take from the outside or the inside, whichever is the most convenient, and get a true metal thickness measurement in that point. It's used instead of, or as well as, the hammer. I know a lot of people still like using a hammer, and that does give you an indication of the metal thickness. And of course, if you hit it hard enough, it does sometimes go through, and it indicates to you that you do have a corrosion problem, of course. But the thickness gauge, I think, should be used as well as the hammer, because it gives you a quantitative measurement, and you can compare that with previous year's measurements or previous surveys measurements, or in fact watch or monitor how much the material is corroding over time. So how does it work? Well, all the probes have a piezoelectric crystal on the face of the probe, and effectively what this is a small crystal, and when you apply a voltage to it, it causes the crystal to vibrate, and when you apply a movement to the crystal, it in turn gives off a small voltage. So we can use this to our benefit by applying a voltage which vibrates the crystal and effectively sends ultrasound down into the material. And then as it travels through the material and reflects off the back wall, it comes back to the crystal and in turn vibrates it, and that then gives off a small voltage. And we measure the time it takes between giving off the voltage and receiving the voltage. And by doing that, we can very accurately measure the time it takes. Now, it's important that all ultrasonic thickness gauges are calibrated to the velocity of sound of the material we're measuring. And the simple calculation we use for measuring the thickness is, as you can see there, D is the thickness, V is the velocity of sound of the material, and T is the time it takes for the ultrasound to travel down through the material and back again. So all materials have different velocities of sound. Even different billets of steel made in the same foundry can have a different velocity of sound to each other. And of course, the accuracy of the gauge is only as good as the calibration of the gauge in the first place. So as you can see from the formula, the thickness is the velocity of sound times the time it takes to travel down and back up again, which is obviously why we've divided it by 2. as I said a minute ago, mild steel has a velocity of sound typically around 5,920 meters per second, and you can see that in the center of the table here. Aluminium can have a velocity of sound up to 6,360 meters per second, depending on the type of aluminium it is. And GRP, as you can see down the bottom, has a velocity of sound of 2,330 to 2,430 meters per second. So you can see there's a variety of velocities of sounds even for the same materials, and it's always important that you do calibrate the gauge to the actual material of the vessel that you are inspecting to ensure that you've got the correct calibration of the gauge set. All of our gauges we send out set to 5,920 meters per second, which is tends to be a standard figure that works for most vessels. But as I say, it's important to actually calibrate it for the type of the actual vessel you're measuring. Softer materials such as bronze and copper, as you can see, have velocity of sounds of much lower, 3,500 and 3,600 meters per second. So on the right here is a very simple diagram just showing a chunk of metal or a block of metal. And typically, of course, in the surveying world, most of these vessels that we are surveying are coated, and for a very good reason, to stop the corrosion in the first place. The velocity of sound of coatings is around 2,000 meters per second, and you can see here from this diagram that the velocity of sound of the coating is around about a third of that of the steel underneath. So if you're using a ultrasonic thickness gauge, which is calibrated to steel at 5,920 meters per second, the ultrasound will effectively travel through the coating at about a third time slower than that of the steel underneath. So if that coating on top there was 1 millimeter thick, for example, it would show a thickness reading in addition to the metal underneath of around 3 millimeters, which is obviously an inaccurate reading. So in order to take readings traditionally with single echo equipment, the coating had to be removed. And of course, there's three ways to overcome coatings. The first, as I just said, is to remove them. The second is to use an A-scan gauge. And the third option is to use multiple echo, which some of you may have already heard of. So if we just analyze those individually, obviously removing coatings is time consuming and costly. If the coating is a good coating, solidly adhered to the surface, there is actually no need to take it off. Of course, if it's already in a poor condition and starting to flake, then it's not doing its job anyway. And in this situation, then it is, it wouldn't be so much of a problem to remove it. But if you've got a good coating and you don't have to remove it, then of course it would be better not to. And of course, if you do remove a coating, then you'll never get the same quality of coating afterwards once you've reapplied the coating and patched up the area where it's been removed in the first place. Of course, most coatings are taken off using a grinder, so there is a chance that you may take away extra steel whilst removing the coating, so that's not a positive point. And if you do find that you do have a suspect area, then you will need to take more coatings off around that area in order to take further measurements and to fully assess the area. So all of these factors influence the fact that that removing the coating, if it's a perfectly good coating, is probably not the best idea to do it. Another alternative is to use what's called an A-scan gauge. Some of you may be aware of this already, and effectively what this does is it gives you a type of oscilloscope display which shows the reflections of the ultrasound that you're getting. And this one on the left here is it's a produced one. It's not actually taken from a screen of an A-scan gauge, but effectively shows the red line is the echo coming back from the back wall. Of course, the first echo will be the highest amplitude because it's the strongest, and then as the echoes continue, they lose strength and the amplitude dissipates away until it reduces to nothing at all. So the red line there, which is highlighted or labeled as echo 1, echo 2, echo 3, shows the echo coming from the back wall. Now, of course, if you're looking at all the ultrasound waves that are coming back, you may have a pit in the material, and so you get an echo coming back from that, and as can be seen by the lower sine wave there. And then you get noise involved as well if it's a very corroded metal and the ultrasound scattering all over the place. You may get a smaller echo coming back, which is just going through the coating to the interface. So you can get a number of echoes coming back, and the point of a scan is you need to decipher from that which is actually the wall thickness that you're looking at. So it does work. It's a much more complicated piece of equipment to use than a standard thickness gauge, which does all this automatically for you. It's obviously a lot more expensive, and you need to have certain qualifications to understand that you are actually taking the readings from where you should be taking the readings. So then we have multiple echo, which is an approved technology, approved by class societies when taking thickness measurements on board ships. IACS, Lloyd's, ABS, DMV, a lot of them all specifically state that multiple echo gauges with single crystal probes must be used when doing surveys on board ships. So how it works, this picture on the right hand side shows the ultrasound line spread out for time. So you can see that as the ultrasound travels through the coating, it goes a lot slower than it does down through the metal. And so we measure the time between sending out the initial pulse. It travels through the coating slowly, it then travels through the metal faster, reflects off the back wall, bounces back up again, and at the interface between the metal and the coating, a very small proportion of the ultrasound travels back through the coating, and the majority of it stays in the material, which I'll show you in another picture in a minute. But we measure the time it takes from sending out that first pulse to receiving the pulse back, and we call that timing 1. So that's used as a reference echo, and as you can see, it doesn't depict a true measurement of the metal thickness because, of course, the coating is included in the ultrasound path. So the way multiple echo works is that we actually look at a minimum of 3 echoes. And you can see from this diagram now that timing 2 is the same timing that it takes to travel just through the metal below to the interface point. And so very cleverly that ignores the coatings, and the ultrasound stays within the metal part. As I said earlier, about 93% always remains within the metal, and it reflects back up and down until it just dissipates away to nothing. Bear in mind, of course, this is spread out for time, so the ultrasound is going straight up and down, not in a double-shaped waveform like it's shown there. So the advantages of looking at more than one echo is that it's called the automatic measurement verification system, and it's all very well looking at timing 2, but this could still actually give you a measurement to a flaw in the material or a pit. It's not guaranteed to come from the back wall. So the only way of actually determining or guaranteeing that the measurement is taken from the back wall of the metal is by comparing consecutive measurements. And in this case, time at T2 is compared against T3, and if they're equal, then a measurement is displayed on the gauge. If they're not equal, no measurement is given, and then that way you can be certain that you're not getting any spurious readings, and it gives you confidence in the gauge when you're using it. So as I said, the ultrasound does actually travel straight up and down, and it doesn't travel in nice straight lines like I've shown in the previous pictures. This is a cross-section of a probe with the sound wave going down through the material. It's a different way of showing it, but as you can see there, timing 1 travels through both the coating and the metal underneath. Timing 2 and 3 measure just the metal thickness beneath the coating. It's important to say that at this stage that this technology will only work as long as the coating is solidly adhered to the surface. So if you've got any delaminations or air gaps in the path of the ultrasound, then that will stop the ultrasound in its path. It's always worth knowing or remembering that ultrasound doesn't travel in air at all, which is why we have to use couplants on the face of the probe and behind the membrane, which we'll come on to a little bit later. So, as I mentioned earlier, if you used a single echo gauge, the reading displayed on the gauge will always give you a reading based on the first echo that comes back. And if you've got a flaw in the material, I know this isn't a very good picture of a flaw, but what it's demonstrating is that the ultrasound hitting the pit, or the flaw rather, in the material there, will come back before the ultrasound comes back from the back wall. And this is what will be picked up by the probe, and this is what the measurement will be based on a single echo gauge. So with multiple echo and with comparing the T2 and T3s, you are eliminating any issues associated with flaws in the material. So going back to that oscilloscope picture again, as I say, echoes 1, 2, and 3, they're the maximum amplitude coming back, and that's what we use to take the thickness reading. If you're looking at a single echo gauge, then you're more likely to get one of the echoes on the lower black line there, which of course wouldn't be a true reading of the thickness. Now, one of the points that some people come to us with is the fact that a single echo gauge, because it gives you a reading on the first echo that comes back, means you can pick up a pit on the back wall, which is true. You probably could if you happen to land on top of it. But obviously, if you're measuring a large plate, in order to land on top of a pit would be a very, very difficult thing to achieve. You'd have to take a very small matrix of points over a large plate in order to land exactly on top of it, for the ultrasound to come back or to land directly on top of it. As you can see here, if you did have a pit on the back wall, the multiple echo gauge would show you the measurement based on the red lines. The single echo gauge would give you the measurement based on the blue line, if of course you happen to land directly on top of the pit. So that's worth bearing in mind. A thickness gauge shouldn't be used to find flaws or pits in a material. It's used to measure the thickness, and there are instruments out there on the market which are used for finding flaws. So if that's something that you would like to do, or inspect welds, then a flaw detector is the tool that you should be using to do that job. So this is just showing a picture of a gauge measuring through a very thick coating. The piece of metal there is 12.7 millimeters, as you can see, and there's different stepped levels of coating on there. And I think that coating is around 3 or 4 millimeters, and it's ignoring it completely and just measuring the metal thickness underneath. So that's just showing it in practice. So when we're using multiple echo on corrosion, we have an advantage in the fact that obviously if the back wall is heavily corroded, naturally the front wall will be heavily corroded as well. And when you've got heavy corrosion, the ultrasound scatters a lot more. So it's a misconception by a lot of people that they prefer to use a small diameter probe to get to the bottom of a pit on the front face. As you can see from the top diagram here, that if you did that, of course, the ultrasound still scatters from the back wall, and you have a less chance of the ultrasound hitting the probe, returning to the probe and missing the measurement altogether. The advantage of multiple echo is that you can actually fill the front pit with couplant, and that's ignored as if it's a coating. So you just measure from the bottom of the pit to the back wall, and of course having a larger diameter means that you've got a much better chance of picking up the return sound waves when they've been scattered on the corroded back wall. So the standard probe that we supply, which is suitable for this type of application, is a 13 millimeter diameter probe. We wouldn't recommend a 5 or a 6 millimeter probe, which is what a lot of people come to us and ask for. We're going to talk a little bit more about probes in a minute. A trick, which we call the credit card trick for obvious reasons, is using a plastic credit card. And you must be careful when you do this, that there are varieties of plastic cards out there. Some of them are laminated paper, so make sure you don't use one of those because that won't work very well. But if you have a solid plastic card, you can actually put couplant beneath the card, fill all the pits and crevices and put the card on top. And of course a little bit of couplant on top of the card, and you'll ignore both the card, the couplant, and just measure the metal thickness. And it does help in some situations to just level out the probe and ensure that you're getting a good level probe to pick up those return sound waves. So there's two types of probes available on the market. There's a twin crystal probe and a single crystal probe. I'm not sure if everybody can see my pointer here, but you can see a divide line going down through the probe on the top picture. Excuse me, this is a twin crystal probe, and what happens here is one side transmits the ultrasound and the other side receives the ultrasound. At the bottom is a single crystal probe where it's a flat disc, and it transmits and receives the ultrasound into the same disc. So if you looked at it in a cross-section view, you can see on a twin crystal probe the two crystals are slightly angled towards each other. The ultrasound path, as you can see there, is actually in a V shape. So we're not actually measuring the thickness with a twin crystal probe, we're calculating it using trigonometry, which is the red line in the middle, which is the thickness we're looking at. And of course the angle at the bottom of that V shape changes over different measuring ranges. So it's common practice that if you had a single echo gauge with a twin crystal probe, you would also be supplied with a step wedge of say 5, 10, 15 millimeters, etc. And you should calibrate the gauge to the thickness which is similar to what you will be measuring on the actual job. Of course you can't get it exact, because if you calibrate it on a 5 millimeter step you may be measuring 6 or 7 millimeters, so there's a certain inaccuracy there. It also the angle at the bottom is also affected if you're measuring on curved surfaces, and for that reason it's always recommended that you put the divide line perpendicular to the axis of the pipe or the curved surface that you're measuring, so that the ultrasound angle doesn't get affected by that inside curvature. And in fact, with a twin crystal probe, some of you may have already tried it or know it, but if you put a probe onto a piece of pipe and you rotate it around through 360 degrees, you'll see your reading on your gauge will go up and down accordingly, because the angle's changing on that because of that curvature. So for twin crystal probes, it's commonly known as V-beam error, and it does have a compensation in the gauge to overcome that problem in the first place. One of the advantages of twin crystal probes is it's very good on, or better on, thin material. So, but unless it's very thin, then you get what's called a W effect. With a single crystal probe, the ultrasound travels straight up and down. So the crystal vibrates, it sends the signal straight down. It doesn't matter what the measuring range is that you're looking at. You have a linear accuracy throughout the measuring range. So it's common practice that multiple echo gauges are supplied with just a test block of one known thickness. We supply a 15 millimeter test block. And if you calibrate it on that, then it's calibrated throughout the measuring range of the gauge. As if you're measuring on curved surfaces such as pipelines, you can actually spin the probe round through 360 degrees and there's no inaccuracies as a result of that. So single crystal probes are supplied as what we call soft face probes. They actually have a membrane on the face of the probe. The advantage of this is firstly that the probe doesn't wear down, so you don't have to zero it at all. Secondly, obviously it protects the probe, so you're not going to damage it. And thirdly, it does help coupling the probe to the surface, because it doesn't feel very soft, but it does slightly mold itself to the surface if it's rough, and that means that you get a better chance of getting the ultrasound into the material in the first place. Only multiple echo gauges can use soft face probes, because of course a membrane would affect the ultrasound calibration if you used a single echo gauge. As I said earlier, ultrasound doesn't travel in air at all, so you must make sure that there's no air trapped underneath the membrane, and there's a very thin oil called membrane oil which we use, and you put that behind the membrane and just make sure there's no air trapped underneath when you fit the membrane. So all probes that we supply have a feature called intelligent probe recognition, and the important point about this is that when probes are manufactured, they have upper and lower limits, the same as anything which is manufactured, and they have different gain settings, different sensitivities, etc. All of our probes have a microchip installed in the probes, which stores all of that relevant information, and it means that when you plug the probe into the gauge, that information is transferred to the gauge, so you get a perfectly matched gauge and probe combination, which is obviously better performance in the long run, which is what you're looking for. So probe frequencies. Most probes that we recommend are for heavy corrosion is a 2.25 megahertz probe. The reason for this is the lower the frequency of the probe, the better its performance through heavy corrosion. So but the disadvantage is that you can only measure down to 3 millimeters with it. Now, that would actually be acceptable to a lot of applications where they're looking at sort of 6-7 millimeters minimum, and that's fine. The probe that we normally recommend for marine surveyors to use is the 3.5 megahertz probe, which still works very well through heavy corrosion, but has the advantage that it will measure down to 2 millimeters instead of 3, so you've just got a little bit of extra leeway in the bottom end of the measuring range. We can supply a 5 megahertz probe, but the performance is not as good as a 2.25 on heavily corroded metal. For GRP measurement, we have to use a very low frequency probe, which is a 1 megahertz probe, so that we get that penetration in through the GRP gel. As I said earlier, there's different size probes available. The standard probe that we supply and recommend is the 13 millimeter. So for surveyors, we'd say a 3.5 megahertz 30 millimeter probe. These are all color coded, by the way. So the 2.25 megahertz is yellow, the 3.5 is green, and the 5 megahertz is blue for easy identification. Ultrasound doesn't travel in air, so we must have couplant in the path of the ultrasound at all times. It's better to use the dedicated couplant, but there are alternatives you can use if you're ever stuck. Liquid soap, wallpaper paste, washing up liquid can all be used. They're not ideal. You need to have some sort of liquid which is thick enough to fill all the pits and crevices, but at the same time not too runny. Thin enough to fill all the pits and crevices, but at the same time not too thin that it's going to run away if you're measuring on vertical surfaces. Grease, Vaseline, substances with thick consistency are not very good. They also have a tendency to pick up debris on the face of the probe, so you're constantly wiping that away, and obviously that just to get the better performance. So quite often we hear that multiple echo gauges don't work on heavy corrosion. They do work on heavy corrosion as long as the guidelines are followed. This is obviously you can see here there's a very corroded inside of a tank on an oil rig actually. And this is measuring, as you can see on the display there. And this was a particularly dirty job, and I'm sure a lot of you won't be getting in this sort of state, or I hope you won't anyway, but there you can see the gauge still working even in nasty condition such as that. So water is a very good ultrasound, transmitter of ultrasound, and if you're ever doing a deck and there's puddles, you can put the face of the probe into the puddle and that will act as the couplant. Here you can see there's a bit of sediment in the bottom of a tank, and as long as you move the mud out the way, the moisture itself will act as a couplant and take the thickness measurement. So data logging. Some of the gauges we offer have a facility for data logging, and it transmits the measurements in real time actually using a wireless technology to a laptop. The advantage of data logging is, of course, that you can have a standard template, and you can fill that template up, and you can come back the following year and you can fill in exactly the same places if you're doing the same vessel. The disadvantage of it is that you may not always do the same vessel each time, or the same type of vessel each time you're doing a survey. So, of course, and that is mostly the case in the sorts of jobs that you do. So a data logging can be useful. Some people prefer to use the paper and pen still, but if you wanted to, this data logging software allows you to set up templates in either a grid or a string or a combination of both. So, for example, you may make a grid up down both the port and the starboard side of a vessel of a certain number, say 20 by 4, and then a smaller one for the transom. The measurements are all saved in a text format, and they can be opened in Excel afterwards. But this gives you a simple idea of how the measurements are stored in a grid, and the measurements that you get on the top right, on the top left there. So a little bit about when you can and can't get measurements, because it's important if you are using the equipment. If you're starting to get a reading, it could be for any number of reasons, and it's always difficult if you've got somebody looking over your shoulder and you're not getting a reading, and you're starting to sweat a little bit while you're not getting that reading. So the first thing, of course, is to check the gauge is working properly, and the best way to do this is to check it on the 15mm test block that's supplied with the kit. The reason is because we know that's within the measuring range of the probe. We know that it's a good piece of steel, and we know that if it measures on that, then the gauge is working as it should do. If it's not measuring on that, more often than not, the biggest problem that we come across is where the membrane isn't fitted properly to the probe, and in fact they've got air trapped underneath the membrane. So if you're not getting a reading on the test block, try removing the membrane and just measure directly onto the test block without a membrane fitted with a little bit of couplant. And if you start getting a reading, then you can obviously determine that the membrane is what is causing the problem. So refit it properly, make sure there's no air trapped underneath with a little bit of membrane oil behind the membrane. The next thing, of course, is check you've got the right equipment. So check that the correct probe is being used for the measuring range. We covered that briefly earlier, but if you're trying to use a 2.25 megahertz probe and measure 2 millimeters, it won't give you a reading because, of course, it is below the measuring range of the probe. Ultrasound doesn't travel in air, as I've already said. So if you've got any coatings which have become delaminated and aren't solidly adhered to the surface, then of course there's air trapped underneath. This is a particularly bad example, and you wouldn't dream of trying to measure through that anyway, I'm sure. But you have to be careful because the coatings can sometimes be delaminated, but from the outside they actually look like they are, it's a good coating. So bear that in mind, that the coatings, there shouldn't be any air in the path of the ultrasound, and they should be solidly adhered to the surface. There are certain coatings which cause problems that we're aware of. Some copper anti-fouls with very high levels of copper can cause problems. The reason is because the little particles of copper which are in the coating act as reflectors, and so they reflect the ultrasound back away or in different directions away from the probe. Layered or solid coating, so in other words, if you've got different layers, then the ultrasound can actually reflect or bounce off of those individual layers. So it's important that the coating should be a solid coating rather than layered. And coatings with tiny balls of air, I can't remember what these are called, but it's a type of coating used as a filler. I'm sure a lot of you are aware of these. It's a lightweight filler, and of course the little balls of air will cause the problems. I think they're called microbeads or something like that. So they will cause problems with the ultrasound as well. The next thing is check the geometry. So it's important that the front and the back wall should be parallel with each other. Of course, if you've got a back wall which is angled to the front wall, the ultrasound will reflect away and not come back to the probe. So this may be a problem if you're trying to measure an engine, for example. From the outside, it may look like it's going to be a nice smooth surface, but the inside geometry means that the back wall is going to be at an angle to the front face, so you're not going to get any readings in that situation. So that's just something to be aware of. It's a little bit of common sense involved with that. With multiple echo, you can't measure down long, thin rods such as bolts. The simple reason for that is because the very first echo which is sent out, or pulse which is sent out, the first echo that comes back will be from the very bottom back wall, as depicted by the black line in this illustration. But of course, it'll also, on its way down to the bottom, reflect off the side walls. And so you'll get other reflectors, such as the blue and the red line, coming back to the probe very shortly after the reflector from the black line does. And of course, because we're looking at the consecutive echoes, this confuses the probe and the gauge, because you're getting more than you should do, more than the number of echoes coming back that you should do. So a rule of thumb is that the diameter or the width of the part you're measuring should be at least 2.5 or 3 times the thickness that you're measuring. And if you follow that rule, then you won't get any ultrasound reflecting off the side walls and affecting the reading that you're getting. So check the surface. Any loose or flaking paint should be removed. Of course, we've already covered that. Dirt and debris should be cleaned off, perhaps with a wire brush, and make sure you haven't got any debris on the face of the probe. So all of these can cause issues with taking measurements. Check the type of material. Some types of casting cannot be measured. The reason for this is because, of course, casting is all thrown into a mold, and it could have bits of grit or metal or other bits and pieces which are thrown in with it. So there's no guarantee that you're going to have a consistent velocity of sound property throughout the body of that casting. So you could calibrate it in one area and then take a measurement sort of 10, 15 centimeters off to one side and get a different reading, because the velocity of sound is different throughout its body. Having said that, we do have success measuring old Victorian water pipes which are cast. So I know that's not in the marine surveying application area, but it doesn't apply to all castings. It is unfortunately a case of try it and see. And multiple echo can't be used on plastic or GRP, and the simple reason for that is that because we're looking at 3 echoes, the ultrasound is absorbed far too quickly in plastic and GRP. The material is far too attenuative. So that leads us nicely on to GRP measurement. As I just said, it's too attenuative to allow 3 echoes, so we have to use single echo technology, which is fine because GRP doesn't tend to have coatings on top of it, so we don't have any requirement to remove those or to ignore them. As I said earlier, when we were looking at the probe table, a low frequency probe is required, and the one that we've discovered to have the best performance is a 1 megahertz probe. So the whole point of it is to obviously assess the condition of GRP, check for delaminations, blistering, or osmosis. So GRP doesn't have a consistent velocity of sound properties, and really the way it's worked is it's used more of a comparative type technology rather than true thickness measurements. It is giving you thickness measurements, but the idea is that you compare it to the local area or the neighbouring area. I always refer to, when I was giving a presentation once, I always referred to one of the surveyors giving me an example of when he lifted out a yacht from the marina on a pre-purchase survey, and as soon as they lifted it out, you could see lots of blisters down the side of the hull. And when he went to go and get somebody to show them the blisters, he came back and they'd all disappeared, they'd all drained away, the water had all disappeared completely, and there was nothing to be seen. So in a situation like that, this gauge would be perfect because it would show you perhaps 6 millimeters in the area around that delamination or blister where the GRP is solid, and then of course where the blister has occurred, you're going to get one of two things. You're either going to get no reading at all because it's below the measuring range of the probe, it's too thin, or you'll get a thin reading because you're measuring to the air gap of the blister. With GRP measurement, obviously if you've got stringers or strengtheners on the back, they may present a problem because the gauge will possibly go all the way through. So with GRP measurement, it is very much a case of using it in conjunction with your expert knowledge as surveyors. So what you're expecting to see and what you should be seeing, the thickness gauge is there really as a tool to assist the decision making that when you're doing your survey. So with GRP measurement, you do have to be careful. Again, it's not 100% foolproof. So you do have to be careful when measuring core GRP. The GRP won't penetrate through the complete structure, but it may be able to measure either side to the core depending on its thickness. So of course, once again, if the inner or outer layers are below the measuring range of the probe, then we won't be able to measure them. But if they are within the measuring range, then we're going to measure just to that core only. When measuring very thick GRP, it's possible that the structure has been formed using layers, and this is particularly around where keels are bolted onto the bottom of the yacht. Tends to be thicker in the region, maybe 25 millimeters, and of course that's made up of layers. So the ultrasound won't travel all the way through something like that. It will only measure two, maybe it might penetrate 2 or 3 of the layers and give you an inaccurate reading. So it's important to be aware of situations like that. As I said earlier, it's the gauge should be used in conjunction with your expertise as a surveyor. So this is just a picture of somebody obviously taking a measurement. You can see getting a reading there of 4.3 on the vessel. Now this is the gauge in action. It's only just this is a piece of marine GRP. You can see there you're getting good solid readings. Around 7.2, 7.3 millimeters. That's just a sample demonstration of it measuring. So this is how it works. The point of it is that if you've got osmosis and you've still got moisture within the GRP, the GRP effectively swells. And so because water is a very good transmitter of ultrasound, we get an oversized reading compared to the surrounding area. If the moisture is drained away, such as the example I gave you earlier with the blisters on the yacht, then you're going to only measure to that gap in the GRP itself. And one of two things will happen, as I said earlier. You're either going to get an undersized reading because you're just measuring that top layer, or you'll get no reading at all because it's below the measuring range of the probe. So here's another video. This is showing the bow of a yacht. If you watch the measurements, you'll see, I'll just get it playing, but you'll see that they're all around 2.6 millimeters. And then as you come back down the very front, you can see that the measurements start to increase. So it shows that there has been some sort of work carried out at that point. So around here, you can see now you're getting 8.3, 8.2 millimeters, highlighting that there's been some work there and there's a thicker GRP level. And then we go back down to 2.5 again. So just to finish off then, we'll take questions in a minute. We at Tritex NDT do sell a number of gauges. We manufacture them all in the UK. We have a GRP gauge, which is just specifically for taking GRP measurements. And that's available as the 5300, which is just a standalone gauge, or the 5350, which is the data logging version of it. All of these gauges are supplied as complete kits. The 5500, which is the gauge you saw the chap in the tank wearing when he was very dirty. This is designed that it mounts on your waist belt, and it's got an LED display so that you can see the display clearly if you're inside dark areas. And it keeps your hands free for climbing ladders and scaffolding or doing rope access if you do the larger vessels. The 5600 is one of the most popular gauges that we sell. It's just a standalone metal thickness gauge for multiple echo measurement. It has a data logging version, which is the multi-gauge 5700. But what we've done is actually developed a gauge called the surveyor gauge, and this is the multi-gauge 5650. And this is designed really because we do a lot with marine surveyors and small boat surveyors like yourselves. This has the benefit of having both metal and GRP measurement. So I mentioned earlier that all the probes have intelligent probe recognition, and what that means is that depending on which probe we plug into the gauge will automatically switch between metal measurement with multiple echo and ignore coatings, or it'll be set up for GRP measurement. And that's all done automatically, so you just plug the probe in and plug and play, as they say. And then there's the multi-gauge 5750, which is the data logging version of that probe. So all Tritex gauges are supplied complete kits and hard carry cases, with 3-year warranty and free annual calibration for the life of the gauge. We just ask that you pay the shipping cost back and forth. And we do offer a 10% discount plus free shipping anywhere in the world for IIMS members as well. So that's the end of my talk. I'm open to listen or answer any questions, hopefully, that you have. If there's any of those parts of that presentation that you wanted to ask me about.
Thank you, John. Yes, any questions from the audience? If you'd like to ask John a question. I would say, whilst people are pondering if they have a question for you, John, I've seen that presentation a number of times, as you know, and I must be the most trained person in Tritex kit, whether they've used it in battle.
Absolutely. You'll be able to do it for me next time, Mike.
Possibly. And I know you're coming up to Scotland on Monday. We're running a small craft training day up in Scotland on Monday, so we'll be in Glasgow, and John's bringing the kids up. We're going to climb under boats and have some more play.
That's right, yeah, absolutely. Yeah, much more fun doing it in practice than sitting watching a presentation.
Absolutely. John, it looks as if there are no questions, so I'm going to say thank you very much indeed. It's been an absolute pleasure to see you as always. I'll see you on Monday. And of course, if anyone does have any questions or wants to talk to you about using the kit, then they've got the contact details on the screen. John, thank you very much indeed.
Okay, thank you, Mike, and thank you. It's been great, and hopefully it will go well for the rest of the 24 hours.
Yeah, black coffee. Take care, John. Cheers for now.
Thank you, everyone.